Hello everyone to the class of Digital Image Processing. Today's topic of discussion is image enhancement. In particular, we are going to understand what is image histogram and how histogram processing would help us to achieve image enhancement. So we are going to understand the basic techniques of image enhancement in spatial domain. What is image enhancement? The different kinds of image enhancement, particularly today about histogram processing, also if possible about point processing and neighborhood operations. So before proceeding further, all this discussion, all the days we have been discussing about the grayscale values, and the usual value of grayscales ranges from 0 to 255, where 0 is indicating a black pixel and 255 is indicating a white pixel. There is no particular reason as why we have to use this particular range, but the studies show that, the survey shows that this basically comes from the display technologies, and for better visualization, these many gray levels are sufficient for a human eye to perceive the images in a good way. So what is image enhancement? So image enhancement is the process of making images more useful. Now what do we mean by making more useful? As we all know, the images carry lot of information. The images convey more data than the words could convey. So that's why there is a popular saying says that an image is worth than 1,000 words. So why we require to do the image enhancement? Following are the most commonly used reasons as to why image enhancement is required. So in certain applications, it might be necessary for us to highlight the details of the region of interest in a particular area. For example, in a medical image, we might be interested in looking at where the tumor is, or we would like to enhance only that particular portion where a block is available. When we talk about medical heart images, when we take, we would like to know such details where clots are present and things like that. Also, image enhancement is useful in removing the noise from images, which will help us to visualize the image in a better way. And hence, this is purely a subjective topic. Some people may prefer to use high contrast images, some people may prefer to use low contrast images. But whatever it is, the images which are more visually appealing, that is helpful for analysis. And to do this, we require or we use many image enhancement techniques and many image enhancement transformations and algorithms. Today we are going to study one such technique. Before proceeding to study the technique itself, we would just understand as to what enhancement is. What are we talking about by taking a few example images? Present it here is an image. This is a digital image, a medical image, where we do not have much details revealed. We subject this to image enhancement or transformation functions, apply some transformation function to this, and after that we obtain this image. And we can see that the portion which was not very much clearly visible is somewhat in a better way visualized. As we can see, this part of the image is not very clearly visible in this image. So after enhancement, such fine details which might be lost out, which our human eye is not able to perceive, such details may be obtained after image enhancement techniques are applied to an image. Let us consider one more example. Here there is an example of a medical image taken. We subject this. You can see here there a lot of details are lost, the ridges and all those details are not very clearly visible. After subjecting this to image enhancement or in transformation functions, we obtain this image, which will give us a better visualization of the images. Here is one more example as to where the image enhancement technique has been applied. This image is of a PCB which is corrupted with noise. Lot of noise present here as you can see. It's not clear, and when we subject this image to image enhancement, we obtain this. This image will give a better visualization of the image. The details can be more intricately visible here for better analysis. So, how are we achieving this? This can be achieved. The image enhancement techniques can be applied in both the domains used for image processing. As we all know, image processing can be done in spatial domain as well as frequency domain. So spatial domain techniques, what we do here is we directly manipulate the values of the image pixels. We change the values of the image pixels. The intensity of the values of the pixels are directly changed using some transformation function. And in frequency domain techniques, what we do is we take the input image, apply some transform function, we convert that input image into the using either Fourier transform or wavelet transform or maybe discrete cosine transform or variety of other transform techniques, and we try to manipulate the coefficients of these transforms, which will lead to the enhancement of images. Now, we will limit our discussion for today in using spatial domain techniques. So, moving ahead, we would like to understand how this processing can be achieved. Enhancement can be achieved using image histograms. So for that we need to understand what is histogram of an image. As we can see here presented, it's nothing but a graph depicting the number of occurrences or the frequencies in the sense how many times a particular pixel value is seen in an image. So how many times, this is the different gray levels present in an image, and each of these gray levels will have how many times that gray level has been seen in the image. That is nothing but the frequency of that particular gray level, and that is the plot of a image having this image histogram. Let us understand this more clearly by taking one example. Here is an example of an image. A grayscale image is taken. Some values here are on a lighter side, some are light gray, and this is little darker grays. Pixels are available here. So there is a lot of variation of intensity, grayscale variation, intensity variations are present in this image. And we would like to know how is the histogram of this image, how many times a particular value has appeared in this image. And the plot of the corresponding image, as we can see here, shows us the distribution of intensity values, the number of times a particular pixel has appeared, and it's fairly good. It's kind of almost uniform. All the pixel values are uniformly spread, although there is some spike over here, but still it's okay. The visualization, for a viewer point of view, the visualization effect is still better. Nowadays we get many cameras which show us the real-time display of the image histogram while we are capturing an image. So here is presented an image of, or the picture of what we want to capture, and its corresponding histogram. This might be useful for various image processing applications. So to get a more better view, let us consider a very simple example, a basic example. Here there are different intensity values from 0 to 15. So 16 intensity values are totally present in an image, and this is the number of times a particular value is appearing in the image, denoted by h of I. So as we can see, there are no pixels in the image having an intensity value equal to 0. So intensity value equal to 0, there are no pixels available. Intensity value equal to 1, there are 2 pixels. So 2 pixels are available in this range. Intensity value equal to 2, there are 10 pixels. Intensity value 2, 10 number of pixels are having the same value in the image. Similarly, 3, 4, 5 have no pixels present in corresponding to these intensity values, and so on. So please note that the histograms present only the statistical information, that is how many pixels are having that corresponding intensity values. It will not give us any indication as to what is the location of the corresponding pixel, at what corresponding position is that pixel available, is not made known to me by the image histograms. Also note one more important feature about histograms. So there might be different images but which may have the same histogram. What do we mean by this? Let us consider an image here. There are 3 different images shown here: image 1, image 2, image 3. And if we are going to plot as seen here, half of the intensity values here are grey and half of the intensity values here are white. Similarly, it is distributed in a different way here also. Out of these total number of pixels, half the value are grey and other half is white. Similarly, it is distributed in a different configuration here, but the number of pixels is the same. So we are going to obtain the same histogram because the statistics is going to be the same. The location of those values are not known to us. So what do we mean by this? Can we answer this question? Can we reconstruct an image from the histogram? Of course not, because we are not having the location information. We only have how many pixels are present and how many pixels are having that corresponding value, and at what location that particular value is available is not made known to us, and hence it is not possible to reconstruct an image from the histogram. So let us consider in more detail as to how to use this image histogram for enhancement purpose. So mathematically, we are indicating the number of levels present in a digital image by h of rk. What does this h of rk mean? Rk is number of the kth grade level, and H is nothing but the histogram of how many pixels are present in that image having a gray level value RK is indicated by H of RK. Having said this, we usually, because the pixels are of varying size, it becomes very difficult to process this different valued pixels. So it is a usual common practice to use normalized histograms. What do we mean by normalized histogram? How do we obtain them? Very simple. We have to divide each of its values, what we get, by the total number of pixels present in the image. So if NK, say for example RK value, for example intensity value equal to 100. The intensity value equal to 100 has 100 pixels. 100 pixels. And my N, here is the size of the picture. The total number of pixels present in an image. If the size is 4 cross 4, for example 100 divided by 16 would give us the estimate or indicate the probability of occurrence of the gray level RK. So the image contrast of a grayscale image, here we are talking about only corresponding to grayscale images, and these grayscale images can be of high contrast or low contrast. What is meant by high contrast images? We have very distinct intensity values present in the image. Low contrast images, on the other hand, very few intensity values. Let us consider an example. So what's a good contrast then? We can see here there are 3 pixels or 3 pictures. One picture having a very poor contrast. We cannot figure out or make out, lot of details are lost in this due to lot of illumination present here. So it's a low contrast picture. It's more on a lighter side. It might be under a very high illumination condition or a poor illumination condition where we have taken this picture, which will lead to a low contrast image. Also we have the same image under different condition. Under a normal contrast condition, we can see the image pixel or the picture is more clear, usually more appealable as compared to low contrast image, and its corresponding histogram is shown here. This histogram is quite narrow, as we can see, because most of the values are on a lighter side. Here it is little more distributed. Equally, the values of gray level and the white pixels are spread out. Even more better contrast picture, high value of contrast is presented here, where we are going to stretch this histogram on the intensity axis using some transformation function. So this is a very high contrast image, and its corresponding histogram, you can see, is more stretched out. Another example is of this image popularly used. This is a famous Lena image which we are using, and we can see the corresponding histogram of this grayscale image. It's kind of fairly distributed histogram, although at some points there is lot of variations present here, but nevertheless it is uniform. I mean, all the intensity values are present in this image. So the image histogram appears like this. Consider one more example. This is an input image. Its corresponding histogram is obtained here or plotted here, and we can see that this image is having lot of dark pixel values. So its histogram is more concentrated towards the darker side. Consider another image. Here there is too much of illumination, and we can see the corresponding histogram is more concentrated on a lighter side. So we do not want to have these kind of skewed histograms either towards the extreme left or towards the extreme right. We would like it to be more spread out. And we can see one more example here. We will see what is the histogram of this. This is limited only to these values. So all these three cases are not the cases of ideal image. The image here, the details of this image are not clearly observed. Now we subject it to different image histogram equalization scheme, and this is what we obtain, the output of the histogram processing. So we can see here more details, more better visualizations. These details, these granules and these grooves, all these is not very much clearly observed in the earlier case. But after processing we can see how this changes. It's a more better view of the image, and we can see the corresponding histogram. We are able to see the distribution more evenly, more uniformly spread out over the entire intensity range. So the same thing is presented here. So this is a histogram of this image. We can see it's on the darker side. This is a dark image, little brighter. The histogram comes on the brighter side. A low contrast picture, it's having a limited histogram, and a high contrast, a better visualization, is having more spread out histogram. So how can we do this? How have we achieved this? There should be some mathematical function behind this which will be able to stretch out the histogram. So we are going to now see this the properties of this transformation function that is applied for this stretching, and the concept is called as contrast stretching. So here we are applying a transform function T, and Rk is nothing but the intensity value. So whenever we apply any transformation to a intensity value, we are going to get a new intensity value, which is the processed intensity value. K is the corresponding intensity range, which lies from 0 to 1. And the histogram equalization, we want to spread out this histogram, and this process of spreading out is called as histogram equalization. And what do we do here? We are using a transformation function T, as already said. R is the input pixel value, and after applying this transformation function, this R value is going to get transformed to a value S. And what are the conditions that this transformation function T has to satisfy? There are two conditions. One condition is that this T should be single valued and monotonically increasing in the interval 0 to 1, because R is normalized and its range is from 0 to 1. Also, this T of R should be spread out in the available range 0 to R or 0 to 1. So here the requirement can be specified that T of R be a single valued is required to guarantee that the inverse transformation will exist, because we have to get back the image also. We should be able to reconstruct the image also, and hence inverse transformation also should exist. And also T of R should be a monotonically increasing function. And the second value says that, the second condition says that we have to spread out this histogram in the entire intensity range. maintaining the darker pixel to remain darker after processing, and the pixel which is on the brighter side should remain in the brighter side after processing. An entire intensity range has to be covered. So the formula for histogram equalization is presented here. Rk indicates the input intensity value. We are going to apply T, the transformation function, after which we are going to get a new transformed intensity value. And what is this P of R and R of J? This Rj is nothing but that corresponding intensity value, the input intensity value. How many such intensity values divided by the total sum of the frequencies is going to give us the new intensity. So understanding this in a pictorial way, this is an image which we want to process, and this is an histogram. As we can see, the histogram is on the darker side. We want to stretch this range, so we apply a transformation function on this range. As we can see here, we are going to stretch out this range. From lower range, we are going to make it little more lighter, 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 and this is a transformation function which is monotonically increasing as well as single valued. And after applying this transformation function, we get this. This is the output obtained, and the histogram here is fairly uniformly distributed. It's quite stretched out, which was highly concentrated here is now stretched out, and this is the output that we obtain after histogram equalization or after applying a contrast stretching function. The same thing is presented here. This is an input image, and after applying the transformation function, we obtain a more uniform output or more uniform histogram. So these are the various functions which could be applied for different conditions. We can choose the different transformation functions, and these numbers show here the outputs that we get after applying these corresponding transformation functions. So applying transformation function 2, we obtain this better quality picture as compared to this original. The second one here, this is the input image. After applying transformation, this is what is the output transformation function. Similarly here, this is the input image. After applying the transformation function, we can see the image here and its corresponding histogram. So here today we looked at what is image enhancement, how it can be performed in the basics of how it can be performed in spatial domain, what are histograms, what is meant by histogram equalization, and we would in the next class solve a numerical based on how to perform histogram equalization, and also we would look at some other processing point processing algorithms and some neighborhood operations that would help us to enhance the images.